Let us discuss about the half-range sine and cosine series. We know we can represent a periodic function by means of a Fourier series, and here we are discussing if a function is not periodic defined over a finite interval, closed interval 0, L, then also we can represent that non-periodic function as a Fourier series of period 2L. Before that, we can discuss about the extension function and restriction function. For that, we consider a subset A of capital R and also a subset B of capital R in such a way that A subset of B subset of R. Suppose that there exists a function f from capital A to capital R and g from capital B to capital R. Now, suppose that f of x equal to g of x. That is, here we are considering A is a subset of B, so B is a bigger set. B is a superset. Okay, here G is the function from B to R. Now here G of x is equal to f of x for all x in A, then we can say G is an extension of f. G is an extension of the function f. In that case, we also say that f is a restriction. F is a restriction of G on capital A. Now let us consider one example. Suppose A is equal to closed interval 0, L, B equal to closed interval minus L, L. And we consider the function f from A to R defined by f of x is equal to x for x belongs to 0, L, and g of x is equal to x for x belongs to closed interval minus L, L. Now here we can see that g of x is equal to f of x for all x in closed interval 0, L. So we can say G is an extension of the function f. Now we can consider another function h of x defined by h of x is equal to mod x, where x belongs to closed interval minus L, L. Then also we can see that h of x is equal to f of x for all x in closed interval 0, L. Here 0, L denote the positive interval. So h is also an extension of the function f. Now let us consider the graph of these three functions now. Here we can consider the graph of f. F of x is equal to x. So here the graph is like this. F of x is equal to x. And next we have g of x is equal to x. The graph is like this. And next is we have h of x. Okay, so here this is the point 0, L. Here it is minus L. So this is the graph of f. Now this represent the graph of G. Here it is minus L to plus L. And h of x, that is mod x, and this is the graph of h mod x. And here we have minus L, and here we have L. Okay, so this is the graph of F, G and H. Here we can see that G is an odd function. So we can say G is an odd extension of F. G is an odd extension of F. And we can see H is an even function. So we can say H is an even extension of the function F. Actually F is defined in the interval 0, L, and we can consider the odd extension in the interval minus LL and the even extension in the interval minus LL. Okay, so these are the two extensions of the given function F. Actually F is defined in closed interval 0, L. Here we can extend the function as odd extension and even extension. Okay, now we can consider the half range Fourier expansion of the function defined over the interval closed interval 0, L. Now here we consider the function f of x is equal to x, and that is defined for all x belongs to closed interval 0, L. And here we can see that this function is not periodic, but it can be extended to an odd periodic function or an even periodic function, as we discussed here. Depending on the type of extension, there are two Fourier series representation for the function f. When we consider the odd periodic extension, the corresponding Fourier series contain only sine terms, and here the cosine terms are missing. That means the half of the series, the half of the Fourier series is missing. So that is why the name half range Fourier Sine series. Similarly, when we are considering the even periodic extension of the function, the corresponding Fourier series contain only cosine terms. That means the sine terms are missing. So that is why the name half range Fourier Cosine series. Okay, now let us move to the corresponding formulas. So first we can consider the half range Fourier Cosine series, and here the half range Fourier Cosine series is obtained by the following formulae. F of x is equal to a0 divided by 2 plus sigma an cos n pi x by L. Here n varies from 1 up to infinity. There is not sine terms. Okay, sine terms are missing. And here a0 is equal to 2 by L integral 0 to L f of x dx, and an is equal to 2 by L integral 0 to L h of x cos, sorry, not h of x, it is given as f of x, f of x cos n pi x by L dx. Okay, now it is enough to calculate a0 and an and then substitute in the corresponding f of x. Then you will have the half range Fourier Cosine series. Similarly, we can consider the half range Fourier Sine series also. The corresponding formula is f of x is equal to sigma bn sine n pi x by L. Here the cosine terms are missing. Okay, and here the bn is calculated by the formula 2 by L integral 0 to L f of x into sine n pi x by L dx. Okay, now using these formulas we can calculate the half range Fourier cosine series. Now let us move to a problem now. Now the question is calculate the half range Fourier Fourier sine and half range Fourier cosine series of f of x is equal to x where 0 less than x less than 2. Here you note the interval 0 less than x less than 2. So this is of the form 0 less than x less than L. So here we have to consider the half range only. So actually the period 2L is equal to 2 here. Here this function is not periodic, even though we can extend this to a periodic function. So we have here actually we have L is equal to 2. This is only half range. Okay, so what is the full range here? The full range is given by 4, not 2. Okay, so here we have this is 4. So L is equal to 2. So it is enough to consider when the question is about half range. You consider the interval of the form 0 less than x less than L. So here we have L is equal to 2 only. Now at first we can calculate the half range Fourier cosine series. Okay, for that purpose we can calculate A0. Now you can write the formula for A0 as 2 by L integral 0 to L f of x dx. Here the value of L is 2. So 2 by 2 is 1 integral 0 to 2 x dx. So here we have, when you integrating, that is equal to x square divided by 2 from 0 to 2. Okay, so here we have 4 by 2. 4 by 2 minus 0. So we have the answer is equal to 2. Similarly, we can calculate An also, and the formula is integral 2 by L integral 0 to L f of x into cos n pi x by L dx. Here the value of L is 2. So 2 by 2 become 1, then 0 to 2, and here we have f of x is x, then we have cos n pi x by 2 dx. Okay, now here we have to integrate this by using partial fraction. So, or otherwise you can apply the easy method, Kronecker method. So here first function x into integral of the second function, that is integral of cos. So we have sine n pi x by 2 divided by n pi by 2. You can put a bracket here. Then minus derivative of x, that is 1, then integral of the sine function. Here we have minus cos n pi x by 2 divided by n pi by 2 the whole square. So the integration is over. Now you can substitute the limit from 0 to 2. Okay, so at first we can substitute x is equal to 2. When you substituting x as 2, you will have here sin n pi, and we know sin n pi is always 0. So the first term becomes 0. Then plus, here we have cos n pi plus cos n pi. Cos n pi is minus 1 raised to n. and here we have n pi by 2 the whole square, that means 4 divided by n square pi square. So the upper limit is over. Now minus of lower limit, here we have to substitute x as 0, so this term becomes 0 and here 0 plus cos 0 is 1, so 4 by n square pi square. Now you can take the common term outside. So what is the common term here? 4 by n square pi square is common. Take it outside. Now the remaining term is minus 1 raised to n minus 1. Now you can consider this as two cases when n is even and n is odd. When n is even, you have here 1 minus 1, that is 0. This is the case when n is even, and you can consider n is odd. When n is odd, this term becomes minus 1, that is minus 2. So minus 2 into 4, minus 8 divided by n square pi square. Okay, now it is enough to substitute the values of a0 and an in the corresponding f of x. Now we have f of x is equal to a0 by 2 plus sigma an cos n pi x by L. This is the general formula for the half range Fourier cosine series. Here we have a0 is equal to 2. So 2 by 2, that is 1 plus sigma n varies from 1 up to infinity. Here we have an. What is an? 4 by n square pi square minus 1 raised to n minus 1. Then into cos n pi x by 2. The value of L is 2. Okay. Now you can take the constant 4 by pi square outside. Now before that, if you want, you can consider the case as even or odd, that we already calculated. So you can consider the case here n is odd. So when n is even, here the answer is 0. So it is enough to consider the case when n is odd. N is odd, minus 8 divided by n square pi square, then cos n pi x by 2. Okay, so this is 1 minus, you can take the constant 8 by pi square outside. Then inside the bracket we have sigma n odd cos n pi x by 2 divided by n square. Okay, now you can expand this by putting n is equal to 1, 3, 5, etc. So we have that is equal to 1 minus 8 by pi square. Now inside the bracket, here we have when n is equal to 1, that is cos pi x by 2 divided by 1 square. No need to write that now. Now n is equal to 3. So cos 3 pi x by 2 divided by 3 square. One more term, cos 5 pi x by 2 divided by 5 square plus etc. Okay, so this is our required half range Fourier cosine series. Similarly, we can calculate the half range Fourier sine series also. Okay, so here we want to calculate our constant Bn only. The formula is 2 by L integral 0 to L f of x into sine n pi x by L dx, and here the value of L is 2, so 2 by 2, that is 1. Then integral 0 to 2 f of x is x, then sine n pi x by 2 dx. Okay, so here we have to integrate now. So x into minus cos n pi x by 2 divided by n pi by 2, then minus, then integral of cos, so sine n pi x by 2 divided by n pi by 2 the whole square. Okay, now you can substitute the upper limit and lower limit here. We have the upper limit is 2, so we have that is equal to, when you substituting x as 2, here we have 2 into, that is minus 2 into, then cos n pi, that is minus 1 raised to n divided by n pi by 2. That is the first term. Then plus, when x is equal to 2, here we have sin n pi, so that is 0. So upper limit over. Now we have to put the lower limit. First term becomes 0 and second term becomes 0. So what is the answer here? So this is equal to, that is equal to minus 4 divided by n pi minus 1 raised to n. That is same as 4 into minus 1 raised to n plus 1 divided by n pi. Okay. So this is the value of Bn. Now it is enough to substitute this value in our Fourier sine series. Okay. So we have the Fourier sine series is Fourier half range Fourier sine series is f of x is equal to sigma Bn sine n pi x by L, where n varies from 1 up to infinity. Now you can substitute the value of Bn here. Now we have Bn is 4 minus 1 raised to n plus 1. 4 minus 1 raised to n plus 1 divided by 4 minus 1 raised to n plus 1 divided by n pi. So n pi. Then into sine n pi x by 2. N varies from 1 up to infinity. Now take the constant 4 by pi outside. Then the remaining terms are minus 1 raised to n plus 1 divided by n into sine n pi x by 2. And here n varies from 1 up to infinity. Okay. Now you can expand this. So that is 4 by pi. So at first you can consider the case n is equal to 1. Then we have the first term is sine pi x divided by 2. When n is equal to 2, minus sine pi x divided by 2. Now the next term n is equal to 3. So plus sine 3 pi x by 2 divided by 3 minus etc. Okay. So this is the required half range Fourier sine series. So this is the method of finding half range Fourier sine series and cosine series. Now similarly, in the same way, you can calculate the Fourier series of the function f of x is equal to x in the interval x belongs to closed interval 0, pi. The only difference is here the value of L is pi, and in the previous problem the value of L is 2. Okay, so you can complete this problem as a homework. Corresponding to this function f of x equal to x belongs to closed interval 0, pi. Calculate the half range Fourier sine series and cosine series. Now let us move to another problem now. Now the next question is, find the half range Fourier sine series and half range Fourier cosine series for the function f of x is equal to pi minus x, 0 less than x less than pi. Okay, and assuming the convergence of the series at x is equal to 0, deduce that pi square divided by 8 equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. Here we are considering the function f is convergent at x is equal to 0. So using this assumption, we have to deduce this series. So at first we can calculate the half range Fourier cosine series. For that purpose we have to calculate A naught. What is A naught? Our formula is 2 by L integral 0 to L f of x dx, and here the value of L is pi. Okay, so 2 by pi integral 0 to pi minus x dx. Now you can integrate this. Now the integral, here pi is a constant, so pi x minus x square by 2. Here it varies from 0 to pi. So that is equal to 2 by pi into pi, that is pi square minus pi square by 2. So upper limit okay, minus of lower limit 0 minus 0. So here we have, this is equal to 2 by pi into pi square by 2. So 2 cancel, 1 pi is cancelled. So we have the answer is pi. That is the value of A naught. Similarly we can calculate An. Now An is formula 2 by pi integral 0 to pi f of x into cos nx dx. So this is 2 by pi integral 0 to pi minus x cos nx dx. So this is equal to 2 by pi, now pi minus x, then sin nx divided by n minus 1 into minus cos nx divided by n square. So the integral is over 0 to pi. Now we can substitute the upper limit and lower limit here. So this is equal to 2 by pi. Here when we substituting the upper limit as pi, here this term becomes 0. So 0 minus cos n pi, that is minus 1 raised to n divided by n square. Then minus of the lower limit, we have to put x as 0. So here we have sin 0, that is 0, then minus cos 0, that is 1 by n square. Now this is 2 by n square pi 1 minus 1 raised to n. Now this is equal to 0 when n is even, and is equal to 4 by n square pi, 4 by n square pi when n is odd. Okay, now we can substitute these values in f of x. Then that will give us the corresponding Fourier cosine series. So we have f of x is equal to a naught by 2 plus sigma n varies from 1 up to infinity an cos nx. So this is already we have a naught is equal to pi, so pi by 2 plus sigma. Here we have n varies from 1 up to infinity, and the answer of n is 2 by n square pi into 2 by n square pi into 1 minus 1 raised to n, okay, into cos nx. And here this is equal to pi by 2 plus, we can consider the case when n is odd only, so 4 by n square pi into cos nx. Now we can expand this. Here we can take the constant outside, that is 4 by pi outside, then sigma cos nx divided by n square when n is odd. So this is equal to pi by 2 plus 4 by pi into, first we have n is equal to 1. So cos x by 1 square. Next we have n is 3. So cos 3x by 3 square. Next we have n is 5. So cos 5x by 5 square plus etc. Okay. So this is the required half range Fourier cosine series. Okay. This is our function f of x. Now we have to deduce one deduction here. So here we are assuming our function is convergent at x is equal to 0. So here we can substitute x is equal to 0. Actually, what is the value of pi f of x? F of x is pi minus x. So we can substitute x is equal to 0 here. When x is equal to 0, we have pi is equal to pi by 2 plus 4 by pi, then cos 0, that is 1. So 1 by 1 square. So 1 plus 1 by 3 square plus 1 by 5 square plus etc. Okay, now you can take this pi by 2 to left side. So pi minus pi by 2, that is pi by 2. Pi by 2 equal to 4 by pi, then 1 plus 1 by 3 square plus 1 by 5 square plus etc. Now you can take this 4 by pi to the left side. Okay, so that is pi by 2 into pi by 4. That is equal to 1 plus 1 by 3 square plus 1 by 5 square plus etc. And here this value is pi square by 8. So that is equal to 1 plus 1 by 3 square plus 1 by 5 square plus etc. And this is the required deduction. Okay. Now here we want to calculate the half range Fourier sine series also. Now let us move to that now. Here our function f of x is pi minus x, and here we want to calculate the half range Fourier sine series. So it is enough to calculate Bn only, and here we have 2 by pi integral 0 to pi f of x into sine nx dx, and this is equal to 2 by pi integral 0 to pi then pi minus x sine nx dx. Now we can integrate. So this is 2 by pi, first function pi minus x, then its integral. So minus cos nx divided by n minus derivative, that is minus 1. Now its integral minus sine nx divided by n square. So the integration is over. Now substitute the limit from 0 to pi. So this is 2 by pi. When x is equal to pi, here this first term becomes 0. Now here it's minus, minus, minus. So minus. And then when x is equal to pi, this term also becomes 0. Then minus of. Here when x is equal to 0, here we have pi. Then here we have minus cos 0, that is minus 1 divided by n. Then minus here sine 0, that is 0. So here we have the answer is 2 pi cancelled. So the answer is 2 by n only. Okay. Now we can substitute this bn in our f of x. So f of x is equal to sigma bn sine nx, n varies from 1 to infinity. So this is sigma 2 by n sine nx, n varies from 1 to infinity. So here 2 is a constant, you can take it outside. So 2 into sigma n varies from 1 to infinity sine nx divided by n. Now let us expand this. So this is 2 into sine x by 1 plus sine 2x by 2 plus sine 3x by 3 plus etc. Okay, so this is our required half range Fourier sine series. Okay. Now we can move to one theorem. That theorem is known as Parsival's theorem. Okay, so this theorem is also known as Completeness Theorem, and here this theorem says, suppose f of x is a 2 pi periodic function defined on closed interval, open interval minus pi with the corresponding Fourier series expansion f of x is equal to a0 by 2 plus sigma an cos nx plus bn sin nx. N varies from 1 up to infinity. Here a0, an, bn are called Euler constants. Okay, then 1 by 2 pi integral from minus pi to pi f of x square dx is equal to a0 by 2 square plus sigma an square n varies from 1 up to infinity divided by 2 plus sigma bn square n varies from 1 up to infinity divided by 2. That is the average of f of x square on minus pi is the a0 by 2 the whole square plus half sigma an square plus half sigma bn square. Okay, now let us move to a problem as an application of this theorem. Now this question is use Parsival's theorem to show that the sum of the series 1 plus 1 by 2 raised to 4 plus 1 by 3 raised to 4 plus etc. equal to pi raised to 4 divided by 90 by using the Fourier series expansion of f of x is equal to x square where minus pi less than x less than pi. Okay, and here for that purpose at first we have to calculate the Fourier series expansion of f of x is equal to x square minus pi less than x less than pi, and we already calculated its value. Okay, and the required answer is f of x is equal to pi square by 3 minus 4 into cos x minus cos 2x divided by 2 square plus cos 3x divided by 3 square minus cos 4x divided by 4 square plus etc. If you don't calculated this Fourier series, you may calculate at first. Okay, after that we can apply the Parsival's theorem. Now by Parsival's theorem, we have 1 by 2 pi integral from minus pi to pi x raised to 4 dx equal to already we have the value of a0 is pi square divided by a naught by 2 is pi square by 3. So pi square by 3 the whole square plus half into, here we have the square of the coefficient of cos terms only. So here the first term is minus 4. So it's a square. So 4 square plus. Now next we have 4 by 2 square the whole square plus 4 by 3 square the whole square plus etc. And here there is no coefficient of sine. All are 0. Now we have 1 by 2 pi integral from minus pi to pi x raised to 4 dx. We can calculate its value. So here we have x raised to 5 by 5, 1 by 2 pi here, minus pi to pi, and its value is 1 by 2 pi, then pi raised to 5 minus pi raised to 5. So 2 times pi raised to 5. So 2 cancelled, 1 pi is also cancelled. So pi raised to 4 divided by 5. Okay, so we can substitute that value in the above expression. So here we have pi raised to 4 divided by 5 is equal to pi raised to 4 divided by 9 plus, you can take that 4 square outside. So 4 square by 2 is there. So 1 plus 1 by 2 raised to 4 plus 1 by 3 raised to 4 plus etc. Now you take this term to the left side. So here we have pi raised to 4 by 5 minus pi raised to 4 by 9. That is equal to 4 square by 2 into 1 plus 1 by 2 raised to 4 plus 1 by 3 raised to 4 plus etc. Now here its value is pi raised to 4 is common. So 1 by 5 minus 1 by 9. So we have 9 minus 5, that is 4. So 4 by 45. So that is equal to 4 square by 2 into 1 plus 1 by 2 raised to 4 plus 1 by 3 raised to 4 plus etc. Okay. Now we can arrange the terms here. Now that is equal to, here we have 1 4 is here, 1 4 we can cancel here. So here we have pi raised to 4 is there. Then here 4 by 2, that is 2. You can take that 2 to the left side. So here we have 90. So pi raised to 4 by 90, that is equal to 1 plus 1 by 2 raised to 4 plus 1 by 3 raised to 4 plus etc. And this is our required answer. So this is one application of the Parsival's identity, Parsival's theorem. Okay. Okay. Now if you want, you can calculate some more examples as homework. So if you want, you can note the questions. Find the Fourier half range Fourier sine series of the function f of x is equal to cos x in closed interval 0, pi. And another question, f of x is equal to c, where c is a constant, in closed interval 0, pi, and also deduce that pi by 4 equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus etc. And another question, find the half range Fourier sine series and cosine series of f of x is equal to x square in closed interval 0, pi. Okay, so let us stop now. Thank you all.